So what we're going to talk about now is gravitation and orbital motion, our last topic. So let's blitz through this. So we should know from last year's physics class is that universal gravitation is the notion that any two masses have a gravitational force of attraction between them. And we learn the equation for that, which is Newton's law of universal gravitation, which is that Fg, or the magnitude of that, and we're going to improve upon that this year, is big G m1 m2 over r squared. And a couple of things about this. Big G is something called the Cavendish Constant, and it is 6.67 times 10 to the negative 11th Newtons meters squared over kilograms squared, meaning it's really, really, really small. Meaning in order to get appreciable size force of gravities, our objects need to be very large, like planetary size, asteroid size, and larger, something like on the order of 10 to the 15th, 10 to the 16th, or larger, in order to get gravitational attractions that are meaningful in scale. The next thing is R. What is R in this equation? This is the center to center distance between the two masses, and that is super important for this. So center to center distance, and we're going to see a couple of implications of that coming up here. M1 and M2 are just the two masses in question. So in other words, if I have M1 and M2, right? So here's 1 and here's 2. The force of gravity of 2 on 1, the force of gravity of 1 on 2, and they would be equal in magnitude because of Newton's third law. Opposite directions, Newton's third law once again. And if I plugged into this, you'd see that I'd be using the same two things. And the R here is from center of mass to center of mass. So another reason why our understanding of simplifications that we've done that treating things as point masses was relevant. We're going to see here when we get to universal gravitation, it actually matters that these things are extended bodies. Okay. So there we go. Let's make this slightly better this year. First off, I'm going to put this into vector form. So the vector form of this would be, well, that big G m1 m2 over r squared is going to come along here. But what I need to suggest here is that this force is always attractive. The way that we do this is by putting a negative r hat on this. Remember, r hat is the radial unit vector. Positive r hat is defined as 1 unit radially outwards. So this literally says radially inwards. So this force always acts radially inwards towards the mass in question, which makes sense. That's a gravitational attraction, pulling everything in radially inwards. So this is a more proper form of this. But even then, that doesn't do it. Not that this will come up during the AP exam, probably not, but I do want to point this out. Notice here, technically what's going on here is every little bit of this mass is attracting every little bit of this mass. So some little bit of this mass, say here, dm, is attracting some little bit of mass here, or this and this and this and this and this and this and this. Technically what we're doing is we're summing up an infinite number of little forces that come together to make the entire gravitational force. Or we can just pretend that they're point masses located at their center of mass, right? So technically, if we're going to be really formal about this, Fg is equal to the negative integral of big G m1 dm over r squared r hat, where m1 would be the mass that is being attracted, and then the dm is the little bit of mass that is doing the attracting. Okay? So we're never going to get into this, but I just wanted to point that out, that there is this idea of adding up a bunch of infinitesimal things that's going to come up in something we'll talk about in a couple of minutes. So there you go, the law of universal gravitation. This is pretty much good enough for most of the work that we're going to do. This is just interesting in terms of the negative r hat because it's going to have implications on the next things that we're going to talk about. So the gravitational force. We know that the gravitational force is a conservative force. Therefore, there must be an associated potential energy function. Well, so far we know that the potential energy due to gravity is mgy. But that is assuming something. This equation assumes a uniform gravitational field, right? It assumes that little g is a constant in that region. So if I'm talking about larger scale here, if this is the Earth, and I'm talking about this is the mass here, that as I go from here to some altitude above the Earth, little g is changing. In fact, little g is diminishing. So let's get an equation for little g. So if I'm standing on the surface of the Earth, drawing not to scale, because that's ridiculous, right? I know that the equation that I use for the weight of an object, which is the force of gravity on it, is my mass times little g. And we just saw that this is magnitude. The magnitude of this force also has to be equal to big G, mass of object 1, mass of object 2 over r squared. So if I combine those two equations, I would see that my mass, so that's the mass of me times little g, is equal to big G, mass of me, mass of the planet that I'm considering here, all over r squared. Now, what is r there? Well, that's a center to center distance. So that's from the center of this object to the center of me. Now, realistically, that's the same thing as the radius of this planet or whatever it is in question, or just really the radius to where I care about, because I could also care about the value of little g if I was out here in orbit, right? So that's the r that I care about. But we're not really going to care about the size of the person, because with respect to the size of the asteroid or the size of the planet, it's negligible. So there have to be a significant distance over Earth for this factor to change. But nonetheless, we get little g in some place around a mass is equal to big G, mass of the thing that I care about, over how far I am from the center of that thing squared. Okay? Boom. So there I have it. And so that is the value of little g. So this equation up here is assuming that little g is a constant in that region. So for small changes in height above the Earth, little g is not going to vary that much, because this denominator is fairly large. So you'd need significant changes in r to have significant changes in g. So near Earth, this is good enough. Well, what happens when I'm in orbit, when I'm out here, where the value of little g might change as I'm traveling around? Well, let's talk back theory about how we can figure this out. So we said that the work done by a conservative force is equal to the negative change in potential energy associated with that conservative force. And so we're going to use this to derive. And this is actually a derivation to look at, because sometimes they ask multiple choice questions that say, like, which of these integrals can be used to derive? Okay, so we know that work is f dot ds, right? So that is f dot ds is going to equal the negative change in the potential energy associated with this conservative force. So this is going to be Fg dot ds is equal to negative delta U. All right, so here we go. What I'm going to do is I'm going to put in our negative big G m1 m2 over r squared. Now, in that dot product there, what that's going to do is, remember that this is times r hat. And so what's going to end up here is ds is technically, dx I hat plus dy j hat plus dz k hat. But here we can do it in polar form instead and make it dr r hat. And that's going to make the hats go away, which is kind of nice. And I'm going to expand this out here, because negative, this is going to be u as a function of r minus whatever some sort of initial u is, right? So that's going to be a constant, a reference. And keep that in mind, because that's going to become important. So what I'm going to do here now is, you notice I can cancel out these two negative signs. Awesome. And so what I end up with here is an integral. And the r hat dot r hat becomes 1, no big deal. So big G m1 m2 over r squared dr is equal to u of r, which is, that's the function we're looking for, minus some sort of initial condition. Now, let's talk limits of this integration. So here, this r that goes with this is going to be what ri is, because technically I could say also this is sort of the reference, right? So that's ri, and we'll establish what that is, and that's just r. So we said when we were deriving this for gravitational potential energy here, that yi is just where we're going to declare u is equal to 0, because it was convenient for the problem as the place of lowest potential energy. This becomes more problematic when I'm talking about in a universal sense, right? Because here, on the surface of the planet, right, technically there is a force of gravity because I can't go all the way in here into the center of the planet. So we need to establish a place where UG is equal to 0. And I don't want to do this at the surface of the planet, because if I'm on the surface of this planet, and we're talking universal, if I'm on the surface, if there's another person on the surface of another planet, then what happens if they make UG is equal to 0 on the surface of their planet? It's too confusing. I need a universal place where UG can be equal to 0. So remember what that says. UG be equal to 0 is saying that this is a place where there is zero capacity of that force to affect the environment at that location. So where can I be such there would be zero capacity? And hopefully what we can think about is this equation that if I go really, really, really far away, like the limit as r approaches infinity, so infinitely far away from things, I can say at that point, that's when there is no force of gravity, right? Because gravity is this universal force. So I have to be infinitely far away from something to not feel gravity with respect to an object. So that's where we're going to make UG is equal to 0. We're going to make a definitional argument here, and we're going to say the gravitational potential energy is equal to 0 at infinity, okay? And that's just the way we define things. So in other words, what's going to happen here is this is going to become infinity, and that is going to then go to 0. Now I have a nice simple integral to solve because I know that big G, M1, and M2 are constants, so they're just coming down. Big G, M1, M2. The integral of 1 over r squared with respect to r is negative 1 over r, and that's between r and infinity. I know this is an improper integral, and if that bothers you, go be a mathematician. But physicists are fairly comfortable with improper integrals. So if I evaluate this, this becomes big G M1 M2 over the r in question minus big G M1, or is it minus big G M1 M2 over infinity, which is equal to that. And if you think about this thing, because the denominator is infinite, collapses to 0, and we get the nice equation here that the gravitational potential energy in a universal sense is big G M1 M2 over R. We can box it. That is an equation that that you need to know, right? And that negative sign is super important. We'll look at implications of why is the gravitational potential energy negative? Like, what does that mean? But it is. Remember, because energy is scalar, right? So something with an energy of 0 has more energy than something with an energy of -1, has more energy than something with an energy of -2, etc., right? It's just a scalar degree. It's all depending on where you set your 0 point. Because we set our 0 point infinitely far away, this is the consequence of that decision. And it's actually going to have some very logical and interesting implications when we get to talk about orbital motion. So there we have it. We have the universal gravitation law, and we have energy associated with it. So what we're going to do now is circular orbits. And then in a separate video, we're going to talk about all the rest of the stuff, just so this is bite-sized and digestible. So let's deal with satellites in circular orbits. That's nice because that means that RR is constant. So let's have a mass there at the center, and let's have our satellite, which is functionally a point mass, okay, be out here. And so we know our satellite is going at a constant radius here. And just to bring up a couple of things, as I said before, this is the altitude. Here's the radius of the planet. We tend to use capital R for that. So in this case, little r, which is the orbital radius, because remember it's from center to center, is going to be equal to the radius of the thing at the center plus the altitude. So that's just something that pops up every once in a while. And we know that this object is going around in that circle because of the force of gravity, the attraction. At any given point, this thing has a speed that is tangential to the path that we'll call VSAT, the orbital speed of the satellite. So now here we go. So you need to know this derivation because it pops up sometimes in multiple choice. If I do a sum of forces in the radial direction for the satellite, that's going to be equal to mass of the satellite times the radial acceleration of the satellite. Here, this is just Fg, right? So that's just the force of gravity on the satellite. So mass of the satellite times AR. Once again, that is the centripetal acceleration because that's the thing that's changing the direction of the satellite as it goes around. So that's V sat squared over R. Normally we would say V tangential because the satellites or speed velocity is tangent to this orbit, kind of the same thing there. And so therefore, using an in as positive declaration, so I'm not getting into the R hats with this, but big G M. So this is the mass of the thing in the center, the planet that I'm orbiting, right? So I'm just going to make a little symbol here. M circle dot is the mass being orbited, not the mass that is orbiting. That's M sat, right? So that's going to be big G, mass that is being orbited, mass of the satellite over R squared is equal to mass of the satellite times V sat squared over R. One R cancels, the mass of the satellite cancels, and we end up with a very interesting equation, which pops up all the time here, that the orbital speed of a satellite in circular orbits only is big G, mass of the thing that you're orbiting, over the orbital radius. Boom. So there you go. The closer in you are, the faster you go in order to achieve that orbit. And the speed of the satellite goes around, depends upon the mass of the thing that you're orbiting, right? So there's a stronger gravitational pull. It's going to make it orbit faster around in order to maintain that orbit. And the interesting thing about that as well is that every satellite at the same radius would have the same orbital speed. So if I had another satellite at the same orbital speed, those satellites would never collide with one another as long as they were in that path, because they would all be moving at the same speed around that path. So there you go. Now, and once again, this is only for circular orbits. Don't over extrapolate that. Circular orbits only. Now, on the line of circular orbits, we could also say that if it's a circular orbit, then you can just talk about distance over time. So that means the orbital speed of a satellite in its circular orbit is also 2 pi r, which is the circumference, over period, which is the amount of time to go around once. So that's the distance to go around once divided by the time to go around once. So that's cool there. And therefore, I can then combine those two to say that the orbital speed of a satellite is equal to the square root of big G, mass of the thing at the center, over r, which is equal to 2 pi r over the period, right? And so looking at those, I can square both sides to get big G, mass of the thing at the center, over r is equal to 4 pi squared r squared over period squared, and then rearrange that. So big G, mass of the thing at the center, all over 4 pi squared is equal to r cubed over period squared. We can box that because that's important as well. So what does that say? That says that if I have multiple masses orbiting the same mass, okay, that this object, we'll call it object 1, and this object 2, that the ratio of r cubed 1 over period squared 1 has got to be the same thing as r cubed 2 over period squared 2, because if you notice, both these things have to be equal to big G, mass of the thing at the center, 4 pi squared. This is a constant, right? So that means that this ratio is true for any two things that orbit the same thing, which is a really interesting, it's actually a very basic idea, because look at what it says. If R1 is bigger, so it's further, well, actually, if R2 is bigger, which it is, all that means is that T2 is going to be bigger as well, but not by the same amount, right? The further you are from what you're orbiting, the longer it takes to go around. That's the conclusion there. For people who did a little bit of history last year, this is actually a proof of Kepler's third law. Okay? Kepler argued that all things that orbited the same thing had this r cubed over t squared ratio as a constant. So there you go. You have your equations for circular motion. Now, one last thing that I do want to do about circular orbits is I want to talk about energy in circular orbits. Well, the total energy of an object in a circular orbit is going to equal its gravitational potential energy plus its kinetic energy translational. Now, if our satellite like for example, it's the moon. The moon is technically also rotating as it translates around. So that would actually have also a KER term. But right now we're going to treat the satellite as a point mass, so it's not going to be rotating just for simplicity's sake. So that's going to be negative G, mass of the satellite, mass of the thing I'm orbiting, all over R, right? Because we said that that is the potential energy function we're using when we're in orbit, plus 1/2 mass of the satellite, V of the satellite squared, right? But we happen to know for an object in circular motion, an equation for what its orbital speed is, which is the square root of big G, mass of the thing in the center, over R, quantity squared. So if I play that out, then I get negative big G, mass of the satellite, over R, plus, and if you look at this, you end up with big G, mass of the satellite, mass of the thing in the center, over 2R. Now that's gross. So what I can do here is just, I get a common denominator, 2 over 2, right? And then I just have negative 2 of these things and 1 of those things. And what I end up with is negative big G, mass of the satellite, mass of the object that you're orbiting, all over 2R, where R is the orbital radius. So there is the orbital, or the energy, total energy for an object in circular motion around a planet. And you will notice that that total energy there is negative. And in the next video, I'm going to comment on why is that total energy negative. So that's everything you need to know about the basic idea of universal gravitation, the derivation of gravitational potential energy in the universal sense, as well as circular orbits. So we're going to come back and talk about what this looks like if we are no longer in circular orbits.